Okay, so let's get started. A little late, but still within academic time. Eh, Let me start with the territorial acknowledgement. The University of Waterloo acknowledges that much of our work takes place on the traditional territory of the neutral Anishinaabe people and Haudenosaunee people. I think I'm getting better at this. Our main campus is situated on the Haldimand Tract, the land granted to the Six Nations. That includes 6 miles of each side of the Grand River. Our active work towards reconciliation takes place across our campuses through research, learning, teaching, and community building, and is centralized within the Office of Indigenous Relations. So with that said, let me introduce our speaker. He's a former, Amir Miraga, which is a former student of my group. Most of the group is here, so it's an honor to have him back. Oh, it's not working? Oh, maybe I'm not talking close enough. Okay, sorry about that. So I was saying, let me introduce Amir Miraga, which is a former student from Waterloo. He was with us for a few years as a PhD student and as a postdoctoral fellow, doing wonderful work with one of my best students. So I'm very honored and happy to have him back and agreeing to make this presentation quite relevant to the work we do at WISE. Amir, I'm going to just speak from what I know about Amir. Besides being an outstanding student and researcher in our group, he then went to work with General Electric. Unfortunately, we lost him to General Electric because he was still working with us, and we wanted to keep it around, but he worked for General Electric for a few years, focusing on microgrids. The work that he was doing when he was a PhD student was focused on electric vehicles, hydrogen economy, hydrogen vehicles, energy. I remember all of this work we did, pioneering work in energy systems, energy hub systems. So that's what started later became the Energy Hub Management System, which we worked with Ian for a few years. So he was one of our starting points for all of this research. And then he went to work with General Electric for a few years in microgrids. He became an expert on an actual practical applications of microgrids. So at that point was a pioneering work because now you hear everywhere, but at that point when all of this started, when he was working on these, was relatively new. Then he went to Singapore, working in a company, then his own company, and then eventually working at the NTU, in the Energy Research Center, correct?
Yes.
And eventually decided to come back to Canada because of family reasons as well. And now he works for Schneider Electric, working different aspects in a management position in the area of microgrids. Hopefully I gave a good overview of your work. And he's agreed to give us a few ideas, a lecture on virtual power plants, which is part of the work that Amir is now focusing on tonight. Thank you very much, Amir, for being here.
Thank you.
The floor is yours.
Thank you so much for the nice introduction. Great to be here. Every corner of this place brings back a torrent of memories here. So incredible to be here. Thanks very much for your interest. Actually, we are diving into a topic that used to be as fictional as flying cars 2 decades ago, but thanks to huge amount of progress in the IT/OT technologies, again in the past 20 years, that science fiction tends to be a reality, knocking on our doors to become a reality. And so I'm going to discuss this virtual power plant. I would call it virtual game changer in the energy domain that is ready, or I would say to be conservative, almost ready to be our reality as well as our morning coffee. Okay. So with that introduction, so before I just give you a present state of status of power system. Just following on the previous, brief introduction of virtual power plant, I would say that if you go to Google Scholar, you see that the oldest publication in this area goes back to almost 2003. Okay, it makes sense. For example, for the microgrid area, it was 1999, 2000. Then microgrid CERS concept at the University of Wisconsin around 2003, 4, 5, 6. So it makes sense. I couldn't find any publication older than 2003. So the first publication started around 2003. We had a peak around 2007, 2008. And most of the major companies in the area of virtual power plant started back in 2009, 2010. So it is not very, very long. But and most of them started with demand response. So most of them was demand response. Providers, and over the time, they add the flavor of some kind of data analytics, software to turn it from demand response to DER program to virtual power plant stuff. So with that introduction, just let me spend a bit of time, because it is all about DERs, distributed energy resources. Okay, so let me give you a bit of just the present state of power system. We are aging. We are dealing with aging energy infrastructure. You know that, and we are experiencing higher demands and lower reserve margins. Of course, we are experiencing more and more natural disasters and potential terrorist attacks, and we see that uncertain stochastic generation and demand are spreading to our power system, and the problem with those, the renewable power sources or electric vehicle is not just because of their intermittency or stochasticity, because utilities are, because we don't have any observability over this area. This is the major issue, not intermittency. It seems that utilities are dealing with the territory, keeps expanding, but they have very limited observability and control over this area. This is the major issue. And of course, emerging new types of loads sensitive to reliability and quality of power, for example, data centers. Okay, in this context, we are experiencing these challenges, major challenges, in terms of reliability, resiliency, efficiency, sustainability, flexibility, and security. So we have these 6 major challenges. But the good news is that we have new capabilities, opportunities, and tools. The first one, optimization and control algorithms. Compared to, for example, 50 years ago, the performance of your CLP, your solver, optimization solvers, the type of MIP problem that you used to solve, back, 15, 20 years ago is not comparable to the type of, problem that you can solve now. Communication infrastructure, for example, one conspicuous example is smart metering. And so it's spreading around the world. And many companies in this area, they are reducing the time interval frequency of gathering data from the field from 15 minutes, 10 minutes to 1 minute, or even less, so that they can incorporate all those data into some kind of distribution management platform. So, and memory and CPU horsepower. And again, with at least 15 years, I don't go longer. 15 years ago, the type of devices that we dealt with at that time, for example, the first optimization based microgrid controller that we worked on, it was on a platform with a very limited memory and CPU horsepower. It was like, for example, 64 megabyte memory and 300 megahertz CPU. But now for example, every gateway that you touch, you notice that it's a full-fledged industrial PC. It's not comparable. And of course, information technologies that I'm going to spend a little bit more on that part. So we have challenges, we have opportunities as well. Okay, and also we are experiencing evolving standards as well. For example, one Good example is 5047 interconnection standard. For example, in the past, when you had low penetration of DERs, the question was how to protect the utility from the DERs. Okay, but now with the rising penetration of all these DERs, demand response, electric vehicles, storage, and anything, the question is that how to support the utility by the DERs. So we are evolving from grid protection standard to grid supporting standard. So it's a huge, huge change. And it's funny, it's, for example, in the past, we used to go to the west, and now we go to the east in a completely different paradigm. Okay. So that's the reason they say that, okay, so now utilities say that now that you are increasing in terms of volume, don't go because of those right-through capabilities. Please stay and help me during the stress time. Okay. And also evolving policies and regulations. For example, FERC order number 841 and 2222 that says all the U.S. system operators to completely open their energy and ancillary services market to both utility and retail scale, okay, energy storage resources. And of course, some markets are already open to this transition. For example, in PJM, a huge fleet of electric water heaters has been selling frequency regulation, And so in terms of regulation and standards, we see all these changes. So with that said, let me summarize the power system evolution with DERs. I could summarize it in seven major steps. First of all, government push. Governments around the world, it's not just Canada or the US, they have some low carbon initiative. And I'm not saying that they are very genuine in their intention, that they really care about environment. But just let's be optimistic and say that okay, they are very they really mean it, that they want to reduce the carbon emission. So in that case, they promote renewable distributed energy resources to meet their targets. Okay, for example, by 2030 we have to reduce carbon emission by this amount or that amount. So in order to lower the cost of this transition for customers, they open up the revenue stream to DER owners. So it used to be the sole responsibility and revenue earner for utilities, but now they are opening the revenue stream for DER owners. Okay. In terms of challenges, yes, of course, new challenges we have: observability, data integration, big data management, and advanced analytics. Of course, because we are dealing with a huge amount of data. Emerging new entities. In this context, new entities are emerged. For example, distribution system operator, okay? And for example, third-party aggregators, that they aggregate all these tiny DERs and sell it to the market. Developing appropriate tools. In this context, we see new tools are developed, for example, virtual power plant and distributed energy resource management system that, VPP is the core of the discussion today, okay? So the idea is to provide an aggregated flexibility that can be offered to energy markets or DSO. For the case of DERMS, it is for the distribution system operator, or for the VPP to energy market or ancillary services market. New business models and opportunities. Yes, for example, VPPs create collective of DERs for market participation in energy ancillary services. Okay. And the other major topic is standardization and interoperability. So ensures that DERs of various types and form and from different manufacturers can communicate effectively and operate harmoniously in a platform like VPP. So the idea is that we can ingest data from different types of DERs all in the cloud, for example, in a platform like VPP. Okay, so seamlessly integrating all these types of DERs. So in order to go right to the point, that what we mean by virtual power plants. Okay, So this is the traditional power plant. The potential contribution is energy market, day ahead and real time, and also ancillary services market. For example, frequency regulation, spinning or non-spinning reserve, and voltage support. Okay, and the idea is that we aggregate all these DRs, forecast them, optimize and dispatch them, and do exact same thing. Okay, contributing to energy market and also contributing to ancillary services market. Okay, this is the whole idea behind virtual power plant. But who gains from VPPs? First of all, DR owners, prosumers, because a new stream of revenue is created for them. Okay, system operators will be able to run the grid more efficiently and reliably. More reserve margin means higher level of reliability, because you know that you have another types of entities coming into picture to provide ancillary services and contributing to energy market. So that's the reason system operators are happy. And also utilities. Utilities enjoy reduced operational cost because they cut down on the need for pricey peaker plants. Why? Because you are managing load and generation locally. Okay, so then you don't need, or you need less, pricey power plants for peak times. And so that's the reason, because of that you are managing locally. So you impose less stress on the transmission and distribution system, and it eliminates or defer grid infrastructure update or investment. So let me just have an overview of major VPP engines. The first one is forecast engine. Provide short-term and long-term forecast for intermediate or stochastic types of DRs. Optimization-based market engines determines the optimal bids for the various markets. Optimal bids, okay. And optimization-based dispatch engine, after market is clear and commitments are established, it determines the optimal dispatch schedule for different sites, different zones, or different DRs. Okay, and of course communication engine. Without communication, it doesn't make any sense. Okay, reads the DR info in terms of online availability, online status, availability, power, and writes command through IO's gateway using a wide range of communication protocols. Okay, these are the major engines of a VPP, virtual power plant. Okay, because I maybe 1,000 times I'm gonna repeat this word, flexibility. First, let me just explain that what we mean by the term flexibility. Okay, we are in short of power or we are excess power. Okay, so if positive flexibility or off flexibility, it means capability of providing or injecting power to the grid. Negative flexibility or down flexibility means capability of absorbing power from the grid. For example, you have a storage, and you can, for example, charge 300 kilowatt power. 300 kilowatt is the negative flexibility. These are the terms that we use for oftentimes well-known terms in the domain of virtual power plants. This flexibility can be provided by device or assets. For example, energy storage can be provided by a site or zone or microgrid, or it can be provided by aggregate of sites or zones, as you see here. So this question comes up that virtual power plant is an IT-based platform or OT-based platform. So before that, just a quick overview of IT-OT. I think most of you are quite familiar with this concept. IT is all about servers, databases, cloud infrastructure, network devices, data analytics, for example, optimization, forecasting. All these things are, are in the category of IT. And actually, OT operational technology is all about, interacting directly with the actual device, real devices, for example, energy meters, renewable energy sources, batteries, gensets, inverters, edge control, or HMI that, you see some, you read some values from the field. These are all, components of OT. In that respect, I would say a VPP platform is a blend of IT and OT, okay? Because it has elements of those, both domains. For example, IT aspect of a VPP platform, for example, communication, okay? Data aggregation and processing from various sources. It is IT. Or software and algorithm for forecasting and optimization. These are all IT components, okay? For the OT, means interfacing with the actual hardware, for example, PV, batteries, inverters, HVAC system, or direct monitoring and control of physical DERs. In that respect, VPP is an OT platform, okay? But the question is there a scenario where a VPP platform can be considered a purely IT-based platform? If you're not directly, linked with the actual or real device, maybe, there is a different entity responsible for that sector, then maybe we can, call it an IT-based platform because you are not directly reading or writing to the device. For example, another entity, another, company is involved with that. In that respects, we can call it, IT-based, but, in general terms, I would say VPP is, in fact, a blend of both IT, OT platform, okay? Market participation or facilitation, actually, this is one of the most important points regarding the virtual power plants. Virtual power plant, or, a company that develops a virtual power plant platform does not participate in a market. A VPP platform is market facilitator, not participant. This is a very crucial point that we have to be mindful. Okay, and in terms of direct connection to the market, VPP platform usually do not have a direct connection, unless there is a need for a 24/7 asset monitoring. Maybe for example, you have a very critical asset, and market operator needs to have a 24/7 monitoring on that device. Yes, we need to have a direct connection with the VPP platform, but otherwise, no, there is no direct connection. Customers, when we say customers, I mean energy companies, have their own trading tables, and they just need flexibility data from a VPP platform so that they can bid into markets. Energy companies say that, give me the flexibility, and then I can take care of myself. I can take care of this, bidding to the market. And but the VPP provider does not participate in the market. Okay. In terms of this question, who provides optimal bids? Regulatory policies and market rules impact the role of VPP platform in providing optimal bids for various markets. In general, we have these options. VPP-driven bidding, the VPP platform generates some optimal bids. Okay. Sometimes the optimal bids are generated by the energy company, and sometimes it's a cooperative model that VPP platform provides some recommendation. Eventually, the energy company makes some adjustment to those bids. Okay, we have seen all of them, so it is possible. But in general, because of that forecasting and optimization capability, which are core of a virtual power platform, a virtual power plant can generate optimal bids. Okay. But as I said, some energy companies say that we have our own market engine. Just give us flexibility, we take care of that. Okay. Now let me spend a bit of time on just two similar platforms, microgrids and distributed energy resource management system, and explore what the link is. There are similarities, among VPPs, microgrids, and DERMS, distributed energy resource management system, in terms of aggregation, forecasting, and optimization. They all have these three major components. Okay, but there are major distinction that I summarize in this table between microgrid and VPP. First, in terms of size. So microgrid having, you are dealing with a relatively limited number of DERs, of course. But for the VPP, you are managing a large fleet of DERs, okay? Geographic boundary for the microgrid, this is confined to a relatively limited area, very, very confined area. But for the VPP, it is geographically more flexible, potentially covering much larger areas, okay? Autonomous operation. This is one of the major, features of a microgrid that, in case of a grid fault or failure, it can disconnect itself and run by itself, taking care of voltage and frequency, okay? But, autonomous operation for the virtual power plant doesn't make any sense because it's all about grid connection and providing energy and flexibility for the grid, okay? Control infrastructure. For the microgrid, mostly relies on a localized control, especially for critical facilities. For example, if you are your customer is a military base, they avoid cloud connection at all cost because of the cybersecurity. So they prefer to have EMS, energy management system, local, on a piece of hardware, local, not cloud connection. But for the VPP, mostly utilizes a centralized cloud-based approach. And, we're going to explain that. Without cloud, it's not possible to take care of, such huge amount of data. So this cloud connection is an indispensable component of virtual power plant, but for the microgrid, it cannot be there. And enabling market participation, for the microgrid, the primary focus is local support. Local support, the value goes to locally, okay? But for the VPP, the values goes upstream for the energy and ancillary services market for the system operator, okay? Okay, so regarding DERMS, now let me, just briefly explain DERMS, that what are the similarities. Of course, similarities, I already explained that, in terms of forecasting, aggregation, forecasting, and optimization. But for the DERMS, distributed energy resource management system, what are the differences? First of all, I have to say that, there are different flavors of DERMS, okay? Utility DERMS, a version of DERMS developed for the third-party aggregators. There are different flavors in terms of the boundary of operation. There are many things, but what I'm explaining here is just a very overall overview of the DERMS concept. Okay. Here we have old power PV forecast here, you see, and then the new forecast coming in. And we notice that, the new power forecast we have, for example, this one, more than what we forecast, okay? And then when we do some kind of, network analysis, we notice that, for example, on this point, we have between 9 to 12 that we have this extra power. So we have the risk of backfeed power and voltage rise issue, okay? At this point, the network analysis shows you, okay? So in that case, what DERMS does is that in order we have to kind of, take care of this surplus power, okay? In order to take care of that surplus power, then DERMS runs an optimization problem and says that, okay, you have to connect this microgrid to absorb more power, and in this aggregation area, you have to disconnect the CHP, and in this aggregation area, you have to increase charging so that, you have. And also for this PV, you have to curtail so that you kind of take care of this surplus power. This is what DERMS does, okay, in general, generally speaking. So operation domain for the DERMS limited to distribution system. It is only for the distribution system, okay? But VPP, it is not limited to the distribution system. It can be transmission distribution. Primary user of DERMS is utility or distribution system operator. But for the VPP, it is energy aggregators that they can operate independent of utilities. Okay. Type of platform for DERMS, it is operational. Okay. But for the VPP, it is more market-driven. It's all about making money, okay? So when we say utility DERMS, utility is not in the business of making more money from these DERs. In fact, it's the opposite side. It's the revenue deconstructive for the utilities. But it is only for the operational, so that, okay, I have to take care of my voltage profile, that if I have this amount of renewable power penetration in my system, I have to take care of my voltage profile so that always should be within certain limits. This is operational, okay, not making money. But VPP is all about making money, contributing to markets. Reliance on other platform or system tools, DERMS, yes, of course. As I explained in the previous, you have to have some sort of network analysis. Okay, but for a VPP, it doesn't care about any powerful equations or network analysis, so to speak. Okay, and major use cases for the DERMS: voltage regulation, peak load management, congestion relief. But for the VPP, the major use case in generating optimal bits for participation in day-ahead and real-time energy and ancillary services market. Of course, when you contribute to these energy markets and ancillary services markets, you are indirectly, contributing to voltage support and, peak load management, congestion relief. But the primary focus is not those operational issues. Okay. So let me explain different entities, involved in a virtual power plant. First of all, you have here, customer area, for example, energy companies, okay, owning these DERs, and they have, a service point. You can think about service point as a physical location that, there is a meter in there measuring net load, and you have a dedicated gateway for each zone or microgrid here, and so you have your VPP platform, VPP provider, okay? So a company provides this VPP running in the cloud, and you have your energy companies owning these DERs, and so this VPP nominates some flexibilities for the trading desk of energy company, okay? And then they bid into market, market is clear, bids are accepted, and then they receive flexibility commitment. Then you are on the hook. You have to deliver these flexibilities, okay? And then once this flexibility commitment is received, then VPP, based thanks to its optimization engine, optimally disaggregate or distribute that commitment to individual zones or microgrids, okay? This is how it works. And of course, in terms of, other entities here involved, these are involved as well. For example, your VPP platform might be linked to some, enterprise system, utility. For example, CIS, customer information system, or MDMS, meter data management system. They already have the interval meter data, so they can, receive those data through API or something. Okay, and another entity, weather forecast server, they ingest some temperature data, weather forecast data, and also other third parties. For example, you have a company that you are very specialized in, for example, price forecast. Okay, then the VPP platform maybe for that piece of data analytics relies on that the company and develop proper APIs so that they can ingest that price forecast. So these are these are different entities involved in a concept of virtual power plant that we have to consider. in terms of aggregation concept for the virtual power plant, yes, based on that forecast engine, so we know VPP platform can forecast, the flexibility that each site can provide, next 1, 5, 10, 15 minutes, okay? And then summation of all these flexibilities can be the flexibility that can be used to build into to market, okay? In terms of optimization, as I said, when the commitment is established that for example, you have to provide 500 kilowatt flexibility, the question is that what would be the optimal contribution of individual sites to provide that 500 kilowatt flexibility, okay? Then, thanks to its optimization engine, generates for example, C1 optimal, C2 optimal, C3 optimal, and similarly, all these sites receive their optimal set points. So optimization is done in two different levels. First of all, what would be the contribution of optimal contribution of individual sites? And the next level is that, for example, if the contribution of this site, optimal contribution 100 kilowatt, then how that 100 kilowatt should be supported, covered. So at the site level and at the aggregate portfolio level, the two different levels of optimization. Okay. So let's explain a little bit on this optimization aspect. That you have, as I said, you have your optimization at the site level, individual site or microgrid level, and you have optimization at the aggregate or pool of sites or pool of resources level. Okay. With that, maybe you are interested in knowing that what is the optimization methodology. I think based on that concept of forecast stuff, most probably you have guessed that the core of the VPP platform. I'm not referring to any special company, but mostly because it is based on forecast, it should be a model predictive control. Okay, and as you are familiar with this MPC, it's all about making decision for the next prediction horizon for the next 12 hours, 24 hours, or 72 hours. Okay, and rerunning the optimal dispatch every 15 minutes, 20, for example, 30 minutes or 1 hour. So this is how it works. Okay, and of course it is based on some tariff and billing data, configuration settings of DERs, for example, your maximum, minimum, all those values. Energy market rules, for example, in some market you are not permitted to export power to the grid. Okay, so you have to reflect that as here and will be shown reflected in the optimization model. And of course, based on all these forecast values, okay, renewable forecast, site consumption forecast, price forecast, and also site baselines. For the baseline, I'm going to explain in further details in the future slides. And of course, for the energy market utility, flexibility requirement is coming, and flexibility availability will be provided, by this engine. But this part is very, very crucial. That we have to have some kind of real-time adjustment, because this guy makes decision every 15 minutes, every 30 minutes. But in real time, so many things happen. Okay, maybe all of a sudden one diesel genset or one CHP unit become unavailable. Okay, or your forecast is inaccurate. So that's the reason in real time you have to take care of this adjustment between generation and load. So you need some sort of real-time adjustment to take care of that imbalance. So that's the reason we have to have actual DER and load power data coming in, ingested to this platform. Okay. For example, every few seconds, every 10 seconds, we have to ingest this data from the field, so that in very fast loop, we have to just take care of that misbalance. Okay. So with that, let me just explain those previous concepts of aggregate level optimization and site level optimization. Okay. So this aggregate level or portfolio level optimization is done across the pool of sites or microgrid or resources. Okay. And one value stream example is committed capacity. Committed capacity in the sense that all the portfolio, all the sites commit a certain amount of capacity to the for example to the utility, for example, 500 kilowatt flexibility commitment means that at any time this committed capacity, that 500 kilowatt should be available anytime, and all individual sites contribute to respect this constraint, and so the question is that what would be the optimal contribution of each site to cover this capacity at the aggregate level? So we have 500 kilowatt capacity, 500 kilowatt flexibility commitment that should be provided by the portfolio of sites, and the question is that what would be the optimal contribution of these sites? And some sites have bilateral contracts with the utility or DSOs to deliver this capacity. It's a very, very lucrative market, okay? And this is the capacity utilities or DSOs can rely on during stress times. This capacity means that, so let me give you some, the use case or example from a real world one that might explain this situation. For example, you assume you have a the industrial plant, a car manufacturer. Okay, you know that the major concern for this big industrial plant is demand charge. Okay, they decide to put a storage device to take care of this demand charge. Energy company says that you, owner of the industrial plant, don't worry about the energy storage. We provide you the energy storage device. We put it there behind the meter. You don't need to pay a penny, okay? So you can do some kind of energy arbitrage. You can do demand charge management. But you have to reserve a certain amount of capacity for us, for example, 500 kilowatt. Anytime we dispatch the signal, you should provide that 500 kilowatt, okay? So this is the promise that you have to make to the energy company. And everybody will be happy with that because what's wrong with that? It's a very nice win-win situation. And the example is what happened last year. December 8, 2023. We noticed a huge price spike in New South Wales, Australia, and also a similar spike we experienced in South Australia. Okay, you see the typical prices: 320, 139, 64 dollar per kilowatt hour. Okay, more than $14,000. So that's the reason. And they dispatch their dispatch in Australia is every 5 minutes. So that's the reason why I say that's a very lucrative market. So 5 minutes, if you have that 500 kilowatt capacity committed, that provide that I send the signal you can provide, it can be a huge, financial benefit for me. So this is what happened, and I think explained here, for example, around this time we experienced this $14,000, more than $14,000, dollar per megawatt hour, and the forecast was around 50. The forecast was $50 Australian dollar per megawatt hour, but we experienced more than $14,000. Okay. Okay. So that was the aggregate level. Regarding the site level VPP optimization, these are the potential value stream at the site level. For example, time of use energy arbitrage based on multi-tier tariffs, demand charge management. Of course, it depends on the different jurisdictions. Maybe in Spain, in Portugal, in the US, they have different this demand charge management schemes. But in general, sometimes you fix a certain kilowatt or megawatt that you don't have to cross that limit, and offline you play with that, or maybe that demand charge level is decided by the optimization engine. It depends on the platform, okay? And maximization of renewable usage. So this is not something that an independent value stream that you can formulate, but indirectly we can achieve that. For example, if you, for this one, if you set revenue generated by the export to $0, then your excess power of renewable will be used to charge your storage rather than feeding back to the grid. Okay. And also wholesale cost optimization. It is based on the real-time market price. Okay. And through the use of some APIs, we have, for example, VP platform developed some APIs, and with that, makes an API call to ingest that price forecast from some servers, and then can run the optimization for the site level. Okay. So then you may ask that you explain site level optimization, you explain aggregate level optimization. What is the synergy between them? So they are done independently. So what is the deal? Actually, they are traded off against each other. Okay. So they are done within a co-optimization framework. So they are all done at the same time. So it is not sequential. It is not independent. It is a co-optimization. So this demand charge management, local value stream, tariff optimization, local value stream, maximization of renewable usage, local value stream, wholesale cost optimization, again local, but this one committed capacity at the aggregate, all considered in the co-optimization framework. Okay. So this one might be, it depends on, different companies have different, ways of developing virtual power plant. But mainly, this is I think, might be similar to all VPP providers, that they have a main dashboard that shows these major info. So they have, different sites, and they have aggregate, and different hours, you see positive and negative flexibilities available, okay? And of course, this value will be the summation of all the flexibilities provided by the individual sites, okay? And this is the main dashboard for a VPP platform. And for example, if you see here that 500 kilowatt flexibility is available here, then when we schedule a 500 kilowatt flexibility event, okay, at 9 p.m., the optimization engine picks it up and redistributes it among individual sites. So 500 kilowatt available flexibility is there. We schedule an event, okay, a DER event, a VPP event at that hour, and then that 500 kilowatt will be optimally disaggregated to individual sites, okay? So you remember I mentioned baseline, okay? Baseline, okay. So, okay, I wrap it up, okay, I increase the speed here. Okay, so baseline is a proxy for what would happen if we didn't have a demand response program or a DER program, okay? For example, here, if you assume you have a DER event between 2 p.m. and 4 p.m., okay, and this is event start, event end. If you didn't have a DER, the demand response event, your load could be here. Okay, this is baseline, a proxy for what would happen if we didn't have a DER program. Okay, but because of this DER event, your actual load is here. Okay, so you have some kind of load reduction. Okay, so this baseline is forecasted based on historical data, and there are different methods to calculate this baseline. Okay, and a typical post-event notification or email shows the baseline energy reduction info, something like that. That your expected use is this. This is the baseline. Okay, for example, 10.21 kilowatt hour, but your actual use because of this demand response program is this one. Okay, so this is for the demand response, but similar concept applies to the DER program, to the VPP program. Okay. So for the demand response, load reduction is baseline minus actual load, Okay? For the VPP or DER program, it is based on minus net load. Net load is the value that measured by the smart meter at the service point. Okay? So, but the only distinction is that for DER VPP program, we have real-time data because VPP is type of a program which is built upon the concept of real-time data, but demand response is not like that. Okay, so for the DER program, assume you are dispatching every 5 minutes. Okay, we have to calculate based on for any of these dispatch interval as data coming in because it is adapting to the dynamic conditions of the system. It is different from a demand response. Okay, this is the distinction, and actually, so once you have a DER event or you have a VPP or flexibility delivery, you have to have some sort of a measure to to see that how you delivered for this demand response or DER program. Okay, so in that case, we run MMV. We call it measurement verification. Okay, and actually the output is based on an actual flexibility. The output. So we have interval meter data. We run the MMV. It spits out baseline, and this is settlement and incentive. Based on some settlement rates, then we have baseline, actual flexibility, qualified flexibility, and finally settlement amount that will be paid. Okay. So finally, what is happening inside the VPP? I think for the one major part is the user interface. So you have to do some configuration. You have some dashboards, as I just showed you, the available flexibility at the site and portfolio level. Okay. And you have some DER integration module, you are integrating these DERs. It can be a SCADA, for example, Modbus, DNP3, OPCM, QTT, IEEE 23.5, or it can be Kafka message bus, or it can be some API, okay, API-based or SCADA-based. Okay. You have some data analytics, forecasting, optimization, and MMV. You have your database or data lake. And you have a server, for example, SFTP server, that user retrieves nomination from that servers. For example, the energy company retrieves those, for example, in the form of a CSV file, retrieves those nominations from that SFTP server. Or user uploads commitment. The energy company uploads that commitment after the market is clear to the SFTP server. This is what happens. And as the last slide, so navigating VPP critical barriers, I would say, yes, of course, interoperability is a major issue. For example, user-friendly interfaces. These are very selling points, of course. But I would say, the major challenge for the VPP is size and scalability. Okay, and because many of the existing platforms that they promise that we do this and that, when they deal with a very large fleet of DERs, for example, assume 100K DERs, they choke, and that's the main issue: how to ingest, how to save, how to do this on analytics. So I've illustrated this here. First of all, you have to have a reliable communication infrastructure handling high volume of data. You assume that, for example, not one site, you have 100K sites, you have so many sensors, data coming in every 10 seconds, for example, you have to read those values from the sites, a huge amount of data. So how you do big data management? So significant data collection and management, adhering to various regulatory and standard requirements due to expansion into more regions, because it's a concept of virtual power plant. It's not a limited geographical area. Many large areas, each of which having their own regulatory issues, and increased risk of intrusions and cyber attacks, because for each site you have a dedicated gateway, and with each hardware you are opening the door to intruders. Okay, this is cybersecurity issue. Okay, and also finally data analytics, forecasting and optimization. I think most of you are familiar with the optimization. Just to give you a rough idea of the size of this problem, for a single site, if you have grid, a storage, a CHP unit, and load, and PV. Okay, and you are doing this kind of model predictive control optimization every 10, 15 minutes, and you are making decision for the prediction horizon of 72 hours. So number of variables, 5,000 variables. And it is almost around 10K, 10,000 constraints for one single site. And now assume that you have 100K sites. So it's a huge amount of data. How you want to cope with the size of that optimization problem? Of course, there are some sort of decomposition techniques, but still it's a very challenging task. Okay, so it is not just a matter of a single microgrid. It's a huge amount of DERs and sites, and so that's the reason it's a very difficult task. So that's the reason I say size and scalability remains the major barrier for VPP development. Okay. Thank you. I think there are some more, but I think I stop here. If there are any questions, maybe I can explain during the Q&A.
So we have a few minutes. Open the floor for questions. Anybody? Yeah.
Thanks very much for the presentation.
Thank you.
Sure.
And it's been taped.
Uh-oh.
So be careful what you say.
Exactly. Thanks very much for your presentation. I enjoyed it very much. I want to pick up on your last point about the challenge of scalability. And from what I heard you saying and calling it the technical barriers, and I was then, if I heard you correctly, sir, I got a sense of some of those barriers fall into the area of things like cybersecurity and communication protocols and volume of data and so on. And then maybe another cluster to do with policy standards, and I'll add a couple, sort of trust and incumbents' interests and those sorts of things. I guess any reactions on that, but my question is, how can we, in what we do here at the university, contribute to overcoming those barriers you've identified?
Yes. Actually, this smart grid area, we used to, just run Powerflues maybe 20 years ago, 15 years ago, just network analysis, so to speak. But now, thanks to this smart grid area, it's a combination of all these disciplines, computer science or, mathematics. So it is not just one discipline. I think in many fronts, university can contribute. And it is very interesting to note that many successful companies in this area came out of universities. So the inception was at the university. And for example, regarding solving that optimization problem, I think there is a huge potential for contribution from a university, or how to some areas or technical issues that maybe industry guys are in a better position to solve those problems. But in terms of data analytics, I think university can make a lot of contribution in that area. Yes.
Thank you.
Thanks.
Oh, thank you for the nice talk. And
Thank you.
From the university side, and also somebody who does a lot of computation, I'm happy to know more complexity is coming to our tables. So that should make our life even more interesting. But I was wondering on the physical side, does it make to think of DERs as dispatchable without storage? Or I'm a bit confused about it. I can see the curtailment kind of can be done, but can it be definitely dispatchable without storage?
Yes. Yes.
How do you do that?
For a storage device?
No, without storage.
Yes.
Can you consider DER as dispatchable?
Without a storage?
Yeah.
Yes, because there are different types of DERs. It's not just a storage. You have PV that you can curtail, okay, out of MPPT mode. If you have a storage, charging, discharging set points. If you have a CHP unit, again, set point. If you have a diesel genset, again, set point, okay? And but some renewable, for example, wind and solar, mostly or on-off or curtail, or maybe just a negative load. Yes, no dispatch, so to speak.
Okay,
yes.
so you combine all of them in
Yes,
DER.
yes,
Okay.
because we have different flavors, different technologies.
Okay. Thank you.
Very welcome.
Thank you. Any other questions? I have one.
Sure,
If I may
absolutely.
take
Absolutely.
the floor for a second. I attended an NRCan Smart Grid workshop last week about the projects they have developed over the last 3 or 4 years on funding from NRCan for smart grids. And one of the presentations was from ISO and Electra. They have developed this pilot program in which basically they are implementing these in principle through contracts. And one of the issues first of all, they spend a lot of time developing the contracts, fine. You sign the contracts with these aggregators or these individual units. And the problem they were having is that the service that they signed for, in spite of all the issues with compliance, is that only 80% of the time there that they were expecting to be available was available. In other words, 20% of the time what they expected was not there. It wasn't an issue of forecasting, but I mean, what I'm trying to say is that this is very uncertain. I mean, in somewhat forecasting of solar, et cetera, is predictable. But if you include these sort of dares and contracts and issues of energy markets, et cetera,
Yes.
it can become very uncertain, right? And we're talking about just not being there when you need it. So how do you address that issue? You mentioned something about contracts and
Yes,
besides the technical part, right?
you refer to the unavailability of servers or something, I think.
Yeah, exactly. They say,
Yes.
okay, fine, I need you this service, you sign for this, and I expect you to deliver this.
Yes.
Only 80% of the time they got that.
Yes.
20% of the time wasn't there.
Yes. Yes.
And there were penalties and everything, but
Yes.
who cares? The moment you need it, it's not there, right?
Yes. Of course, all of these aspects introduce some sort of challenges, Yes, I totally agree. But, when I said, the major challenge is size and scalability, is that, those issues that you mentioned, there are some solution for that. I'm not saying that, this is quite, straightforward and easy to achieve, but, comparing to the size of the problem, for example, those kind of, dealing with those kind of, variables and constraints, I think size is a very, very, daunting task. But, yes, of course, that's the, distinction between, a VPP provider that, has most of the market, and there are many, many players that, they cannot, secure a contract because of those details. Yes, you're absolutely right.
No, they had the contract. The problem was that they were not delivering.
Yes.
So it's somewhat of a different problem. It's an uncertainty problem that might create a lot of issues with this, right?
Yes.
Anyway, thank you.
Great presentation, Amir. Thank you very
Thank
much.
you.
You mentioned optimization a lot in your talk, and I realize that the scalability is a big issue, especially when we have decentralized type of problems. Just wondering if you are trying to solve these problems using machine learning too. I know machine learning is coming up in the forecasting engines that you have, but solving optimization problems instead of just using regular optimization models and algorithms, just forecasting the solutions using machine learning. Has it been something that industry has been interested in or working on currently or not?
That kind of, AI-based, as you said, mostly applies to the forecasting. Okay, for example, we ingest data from the field every 1 minute, it generates that machine learning-based forecasting engine every 1 minute. It updates its output based on the stream of data coming from the field. That one mostly applies to the forecasting rather than optimization, because this one is a very deterministic type of problem that we have. This MPC engine is quite mature. You know that it's been a long time out there. I don't think that this kind of AI based into the optimization, because in that case introduces another level of uncertainty to the, rather than relying on a model predictive control. Because as I mentioned, it is not just relying on the MPC engine. We do some kind of real-time adjustments that take care of the mismatch. So we have that into factor. But in my view, just relying on a AI base for the optimization core, I think it requires that you run the system for a long time, collecting data, so that it can train itself to come up with new solutions. But I think for real projects, you don't have that luxury of time to collect all those data and train your model. So you have to be able, for example, for the forecasting engine, many of these pioneering VP providers say that we need only 2 weeks so that we can train our forecasting engine. They need only 2 weeks, not more than that. So we cannot say that give us 5 years of data so that we can train our optimization model and then run it. Yes.
Okay, one last question. We run out of time.
Oh, okay. Thank you. Thank you. Thank you, Dr. Flor, for this outstanding presentation. My question is kind of a follow-up of both questions, because you were mentioned for optimization, you get the updated results like every minute. One thing that comes to my mind when we mention about the challenges about the scalability is like the computational burden that we have on these systems. Now, 1 minute, 5 minutes, like 15 minutes, 30 minutes, I think will be okay. But when we talk about 1 minute, 5 minutes, when we come to increases or to scale up, that will increase the computational burden, and especially also because of the forecasting tool that, based on what you're saying, is like the MPCs. If we're trying to solve the problem with scale up, they will be also included, like how can we reduce the computational burden, maybe with tools like machine learning and also AI, so we can just proceed with the, to address the challenge that we have in that.
You mean playing with the you mean playing with the prediction horizon? You mean because
yes. How could we reduce this computational burden that we have, especially for 1 minute, like updates that we have on the signal that we send to the servers?
Okay. Yes, this is typical. We are doing this. It's a configuration setting that you can decide if you want to run the optimization every 15 minutes or half an hour or 5 minutes. So of course, if you select 5 minutes, you are increasing the computational burden. But there are the pros and cons for that. But even if assume you are doing the optimization every half an hour, every 1 hour, but still you are dealing with a very sizable problem, and the size is huge. Still, you need some kind of innovative approach to deal with that optimization problem. As I said, there are some decomposition techniques, but still, you are dealing with a very complicated optimization problem. Yes.
Okay.
Thank you.
All right. Well, thank you, Amir, again.
Thank you. Thanks.
Amir is going to be available for a few minutes, so if you have any questions, please. Okay. Thanks, Amir, again, and thanks for being here.
Thanks.
Thanks.